All right, guys, so 4.3 is connecting first derivative and second derivative with the graph of f, which is the original function, okay? So we have here first derivative test for local extrema. Remember, we already knew how to find the extrema values from the first two sections. So now we're going to use the first derivative to find it as well. It's just another way, right? So the following test applies to a continuous function. Let's call it f of x. So 1, at a critical point, let's call it C. At a critical point C, okay? So A says, if f prime, which is the derivative, changes from positive to negative at C, then f has a local max at C. Okay, so let's give you a visual. So i.e., it says here f prime, that means it's a derivative, okay? So I'm going to draw out this in this graph right now. I'm going to use f of x. Now it says if f prime changes, meaning that it's gonna be the slope, okay? So would you agree that the slope over here is f prime is positive? Then it changes. That means over here, the slope over here, f prime, is negative, less than 0. So that means at a value of C, here's C, let's just pick that one. This right here, C, so f prime of C is a horizontal tangent, which is equals the slope equals to 0. So as you can see right there, if f prime changes from positive to negative at that location, then f has a local max. So you can see that local max is right there. Similarly to, if I were to give you another example, right, an upside down v, just to kind of make a point. And again, this is an f of x function. So as you can see on the left side, the f prime, the derivative, is positive. On the right side, the derivative is negative. So it's changing from positive to negative. So therefore, this is a max. And that's a max at an x value called C. Okay. Now this derivative right here, f prime of C, does not exist. Remember, the critical point can be when the derivative doesn't exist or when it equals to 0. Now B, if f prime changes from negative to positive at C, then f has a local minimum value at C. And very similarly to the first two examples, right? I'm going to sketch out a regular function, and I'm just going to make a little sketch right there. Can you see that we started with a derivative here, a slope on the left side? This derivative is negative, so it's going from negative to this derivative. This slope is now positive, so it's greater than 0. So you can see here is your minimum, and that minimum value, let's call the x location is C. Okay. And same thing, right? We can say, okay, well, f prime of c equals to 0. Now on the right, similarly to the derivative at c doesn't exist, I can easily make an upside down v, and as you can see, make sure we label this is a function of f, not f prime. Okay, so on the left side, f prime is negative, right? The slope of that's negative. On the right side, f prime is positive. So this is a minimum right here, and we just call it at a value of c. So f prime of c here, students, does not exist, okay? So just like earlier, the critical point can be that the derivative doesn't have to exist, okay? It can be 0 or does not exist. Now c, if f prime does not change sign at c, then f has no local extreme values at c. No local extreme value at c. Okay, so what does that mean when it doesn't change at c? So here's x, here's again a regular function, and I'm going to, okay. Well, as you can see here, the derivative of this particular equation is positive, right? It's positive here, and it's positive over here, right? So, and here it's a c value. So it doesn't change it at all. Because it doesn't change it at all, even though it looks kind of horizontal. Well, my sketch is not as horizontal. Let me make it a little bit more horizontal. Okay, so there you go. Okay, so this is a little bit more horizontal. So again, I'm going to go f prime is positive here, f prime is even positive here. And even though this spot right here, students, looks a little bit horizontal or more horizontal than the right and the left of that, so f prime at c is still horizontal, but because the sign f prime did not change, there's no extreme value at that spot. Now I'm going to draw another example. Okay. So let's see if I can make up a negative one that will make f prime of c does not exist, okay? So again, this is a regular made-up function. Let's do a sharp turn and then a straight line. There you go. All right. So as you can see here, this is sort of f prime. The slope is going downward, so that's going to be negative, and then this is also f prime of this is also negative, right? So here's a funky c value here. Even though, right, the slope on the left and right, they're different, but they're both negative. Mind you, this is just a made-up sketch. So the derivative doesn't exist, but there's no sign change, so it's still not in extreme value location. Now on number 2, let's go over. At a left endpoint, let's call it A. All right. If f prime is less than 0 or f prime is bigger than 0 for all x value that's bigger than a, then f has a local max or min, respectively, value, oh, I can't spell value at A. Okay, what do I mean by that? Left endpoint. So the endpoint's always a bit more tricky. So a sketch. So I'm going to f of x, here's x. I'm going to do left endpoint. So here we go. Okay, can you see that's on the left side of my curve? Well, this is saying that if it's on the left side, and I'm going to do another one that's also on the left side. Okay, so x, f of x, and here's the left side endpoint. Whee, like that. Okay, so can you see that both are on the left side here? We have two conditions here. If the derivative is negative, which in this case it is, right? That is f prime is negative, then this right here, students, is said to be a max, okay, respectively. So now on the right side, it says if the derivative is positive, which is greater than 0, then this point right here, students, is a min. So that's why, all right? And the reason they call it A, because normally we label the graph A to B somewhere. So like A to B, like this, okay? And then C somewhere in the middle. All right, 3. At a right endpoint, call B. At a right endpoint, B. Okay. If, let's draw this. There you go. Okay, so if f prime is less than 0 or f prime is bigger than 0 for x is less than b, then f has a local min or max respectively value at B. So again, I'm just going to do similar sketch to earlier. This is an original sketch, and B is over here, okay, because it's the right end, and it says for x has to be less than that. So that means whatever I have to go wee on that side. And then another one, and here's B. This is an x axis, here's a B, and this y is going to be f of x regular, and like that. All right, check this out. So as you can see, this slope right here, students, that derivative, as you can see, must be negative, less than 0. So if that's the case, then based on this definition, if the derivative is negative, this is the minimum, okay? So minimum is that dot. Now, similarly, remember, and it says here, all of the x values got to be less than b. Well, yeah, because this is on the left side, all of that is less than the value of b. Then the slope over here, as you can see, that derivative is going to be bigger than 0 because the function is increasing. So if that's the case, based on your definition, if it's bigger than 0, then it's a maximum, okay? And that is true, okay? So the endpoints, again, is always the more confusing part for students. Use the graph of f prime to estimate the intervals on which the function f is part A, if f is increasing, or part B, if f is decreasing, and part C, estimate where f has a local extreme value, right? So for the sake of simplicity, can we close this dot up? Let's just say, here we go. And let's close that dot up. Because it's more, I want to practice the closed endpoints here. So now that we have, this is the derivative function. So remember, the derivative function is different from the function itself, okay? So A, it wants us to answer increase, okay? Increase, students, I'm going to write in parentheses here, is when the derivative is positive. And then B, it wants us to answer decrease interval, and the decreasing function is when the derivative is negative. And then it says here, C, estimate f has the local extreme value, okay? So C, local max. Okay, now to get a local max, changes f prime need to go from positive to f prime negative. So f prime has to go from positive negative, or endpoints. am I invading the other side? Or endpoints f prime has to be less than 0 when x is bigger than a, or f prime has to be greater than b for when x is less than b. Remember, those are endpoint definition. Now, how about local max? D, not D, because on part C, the one's L min and L max. Local min is when we have the derivative changes from negative to positive, okay, or endpoints f prime must be positive at a, which is on the left side, or f prime must be negative at b, and remember b is on the right side, okay? All right, so I'm spelling out all the definition for you. So here we go. Increase and decrease. Remember, increase when the slope is positive. So increase, this is positive right here, and this is positive right there, okay? So increase is from -4 all the way to -2. And students, you don't have to use bracket here. You can definitely use parentheses, okay? This one is a personal choice. And then union that with increase could go for, what are we estimating this value? Negative, for the sake of simplicity, can we just say -0.5? So -0.5 all the way to, let's call that a 2. Okay, and that's a closed dot, so I'm gonna have a bracket. And again, on increase and decrease, you can use parentheses, except the endpoint if it's closed, and it has to be a bracket. Now, decrease is when the derivative is negative. So this is negative here, and this is negative here. So decrease, I'm going to estimate this x value 1, 2, 3, 4, 5, -5. So -5 all the way to -4, union that with, and that's going to be -2, and we picked a -0.5 earlier, so I'm going to keep with that. Okay, so that's increase, decrease. So not too bad for increase, decrease. Now, the local min and local max is when you kind of have to pay attention a little bit, okay? The instruction says estimate where, that means x location. So x location for L max would be, remember, we're looking for the changes from increase to decrease, okay? Okay, looking for the change of increase. So here's the increase, and it changed from decrease. So we have the first one at x equals to -2. Then again, or, right? Or we can look at the endpoints. Would you guys agree? Okay, so let's look at the endpoints. The endpoint says f prime must be negative on the left side. Is that a negative on the left side? Or f prime must be, oops, that should have been positive. That should have been 0. Positive on the right side. Is this positive at prime? So both endpoint students are going to be your local max. So -2, 2, and -5. Okay, so those are all L max. Now we're going to go to L min. I'm going to write x equals down here. Based on the definition, we're looking for when the derivative changes from negative to positive. I'm going to erase what I circle here. So this is negative derivative and positive. So the first one is x equals to -4. And then again, here's another one, negative to positive. So the next one is -0.5. So -4, -0.5. And then because we already use up the endpoints as an L max, so that's all we have for that graph. Okay, let's try to go on to this one, guys. So this one, I'm just gonna let it go on forever. Okay, just like that. In decimals, if you don't see that it goes on, if you don't see a closed dot, it does go on forever. On this graph here on the left side, the first graph, I just want to make sure I have an example that has an endpoint. So that's why I wanted you guys to close that up. Okay. Increasing interval is when f prime is going to be positive. Well, looks like the entire thing's positive, except that there's a gap right there. So increasing interval is going to be from negative infinity, take a break at 1, and then union that with 1 to infinity. And then decreasing, students, decreasing is when the derivative is negative. In this case, students, because all of it is already in for increasing, then we just don't have any. So NA or nothing left, okay, for decreasing. C, we want L max, we want L min, oops, L max, L min. Now remember, L max is when we're chasing for the changes from increase to decrease. Well, there was never any derivative change, so there's no L max. Well, we don't have endpoint, so none, okay? L min is the same thing. L min is when we are trying to see if there's a change from a negative derivative to a positive. The entire time, the derivative is going to be positive. So none for both. All right, guys, let's start with this one, except that can you change that to number 2? Clearly, I cannot count, right? After example 1, we should go to example 2. So example 2, use analytic methods to find the intervals on which the function is increasing, b, decreasing, and find any local extreme values. So as you guys remember already, increase and decrease, we are going to need the first derivative. So let's start with that. So f prime of x equals negative 6x squared plus 12x, and we are going to set it equals to 0. Let's try to factor out the greatest GCF. Greatest GCF, I'm already using the greatest, and then I added greatest again in the GCF. So take out the GCF, greatest common factor, of negative 6x. We are going to be left with an x minus 2. Set each factor equals to 0. So this is going to come out to be 0. And then this is going to come out to be 2. So we have 2 critical points here. Now we are going to make a number line. I'm going to make 2 number lines here, okay, students? I'm going to make the first number line. Well, let's do f of x first. For f of x. And I'm also going to make another number line for f prime of x. Since we have 2 critical points, I'm going to use both. And remember, whether you guys are graphing f of x or f prime of x, the x location should always be exactly the same. So let's do f of x first. When I plug in 0 for f of x, f of 0, I'm going to get negative 3. So that's below. Then I'm going to plug in 2. So that's going to be negative 2 times 2 to the 3rd plus 6 times 2 squared. So that's 4 minus 3. That's going to give us a value of 5. Then all I want to know now is how about left end behavior to see if it's positive or negative, and right end behavior to see if it's positive or negative, okay? So because it's x to the 3rd, negative 100, negative 1,000, negative 1 million raised to an odd power, that's always negative. But then we are multiplying a negative 2, so this is always positive. And then when you have 100 or positive 1,000, positive 1 million raised to a 3rd, that's always positive. But again, we have a negative 2 in the front, so that's always going to be negative. So currently, I'm going to plot a dot using purple. All right, on the left end behavior, it's always positive. At 0 is negative 3, so somewhere there. And then at 2 is positive. And then we have a right end behavior is negative. So if I have to sketch it out, y'all, it looks like this, okay? From this sketch, you can see that I can see the increase and decrease, but let's check to see if it matches our theory of f prime. So, all right, so ready? F prime of negative 100, f prime of 0, f prime of 2, f prime of right-hand behavior. So f prime is this equation right here, or this, doesn't matter which one you're using. Okay, so if you're using negative 100, okay, to the first one, square that, that's always positive, but there's a negative in the front, then that's always negative. When I plug in 0, they're both 0. When I plug in 2, I like to use this one when I'm plugging in 2, because 2 minus 2 is actually, oh, duh, these are both 0, so what am I doing? Duh, that's how we got 0 and 2. So let's plot it in. Whoops. Okay. And then so that's negative. Then let's plug in positive. Positive 100 squared, that's going to be positive, and then times, that's negative. So guys, now I just have to plug in a value in between 0 and 2. So f prime of 1. Duh, I forgot all about these 0 and 2 came out because we solved for f prime. Okay, so when I plug in 1, negative 6 times 1 times 1 minus 2, so that's going to be a negative 6 times negative 1, so that's going to give me a positive 6. So it's up here somewhere, okay? So if okay, so that's positive 6, okay? All right, ready? A, increasing is when the derivative, right guys, it's positive. I have one interval when the derivative is positive. It's from 0 to 2. So the answer is 0 to 2. B, or if you want to use parentheses, that's okay too. B is decreasing is when the derivative is negative. And I have two intervals from negative infinity to 0 and then 2 to infinity, just like that. C, it says find any local extreme values. Now we can also go back and double check the definition of local max, okay? So so local max, I'm gonna spell it out again because I want you guys to know this really well. Local max is when the f prime goes from positive to negative, okay? Or f prime is negative at the left side, which is, remember, we call A, or, I know there's a lot, f prime is positive at B on the right side, okay? Now, since we don't have left and right endpoint, because this goes on forever, we would be looking at this right here. So we are going to say, okay, is there any location where the derivative goes from positive to negative? Yeah, for sure, right there. Okay, and we plugged it in and we said, okay, well, at 2, we have 5. So L max is 5 at x equals to 2. Now, we also can confirm that as well on the f of x function. So that's why I'm telling you right now, like the more we go in this section, right, in this chapter, the more things you will learn to help you answer previous skills. Okay, you don't have to use everything you've studied, but then now you have options. Then we want to see if you have any L min. Okay, so the L min is when the derivative, right, changes from negative to positive. And I'm not writing the endpoint because we don't have any endpoint. So yes, we do have that. This right here is when we went from negative derivative to positive. So we have one L min at 0. So L min is when I plug in 0 from the original, I have negative 3. So L min is negative 3 at x equals to 0. So those are our local mins and max. All right, guys, so B says y equals x times e to the 1 over x, okay? They didn't give us a restriction on our domain. That means this is going to go from negative infinity to infinity. But, okay, guys, we have a fraction, and this fraction has the denominator of x. So that means we know that the denominator can never, ever be 0, right? So we have to keep that in mind. So because x, the denominator can't be 0, if you guys remember from Algebra 2, when we take the denominator and we say, okay, well, it can't be this value. This is actually vertical asymptote, okay? It creates a vertical asymptote at x equals to 0. So when I'm gonna quickly make this line over here. When we, make a number line for f regular at 0, we are going to have, let's just mark it right now, we are going to have some sort of an asymptote right here. So it's a discontinuity. Well, discontinuity will be a reason that the function will not have a derivative. So let's do the derivative and then see if that connects back to this. Okay, guys? So y prime equals, I'm going to use the product rule. So the derivative of x is 1 times e to the 1 over, 1 over x. 1 over x plus the derivative of e to the 1 over x. All right, let's side work. Where would I put this? How about here? I'm going to erase it. So you guys write it somewhere, okay? We are trying to do the derivative of e to the 1 over x. And as you guys know already, the derivative of e to the x is e to the x, but we have a u here. So u is going to come out to be 1 over x, which is really the same as x to the negative 1 power. So u prime is going to be negative 1 times x to the negative 2 power, which is exactly the same as negative 1 over x squared. Okay, so y equals, if we use u substitution, it's going to be e to the u. So y prime then is going to be e to the u times u prime. So y prime equals e to the u, well, we said u was 1 over x, so e to the 1 over x, and the derivative is negative 1 over x squared. So this right now, students, is going to be negative e to the 1 over x times x squared. So that's my derivative of e to the 1 over x, okay? Negative e to the 1 over x times x squared. Divided by x squared, not times. And then I still have multiplied by u, so that's x left. From here, you can see that I can reduce one of these. So now I have just one x in the denominator. So y prime equals e to the 1 over x minus e to the 1 over x all over x. Well, critical point is when we need to take the function and set it equal to 0. Well, I'm going to multiply by the LCD. So this is times x. What we multiply to the bottom, we multiply to the top. So y prime equals e to the 1 over x times x minus e to the 1 over x all over x. Okay, make sure you guys copy down this u substitution here because it's about to go. All right, well, again, we have x in the denominator, so we know right away x can never ever be 0. So right away, that is a critical point. Okay, so x cannot be 0, which we knew, right, from earlier about having an asymptote at x equals to 0. Then we are going to take the numerator and set it equals to 0 to see if we can find other critical points. They both have e to the x in common, so factor that out. We would have x minus 1 left. Take each factor, and we're going to set equal to 0. So we're going to go e to the 1 over x set equal to 0. X minus 1 equal to 0. Let me move up. All right. Well, any exponential, doesn't matter what you plug in, you would never, ever, ever get 0 for the output. So ignore that. Then over here, our second critical point would be x equals to 1. So students, we have 2 critical points. Let's go and make another number line. I liked using number lines, as you guys already know. You don't have to, okay? So this is f prime of x. So earlier I said I was going to make this 0, and we have another one, so that's 1. So this is 0, and this is 1. Okay, so let's do f of negative 100. We knew that f of 0 was not going to exist, okay? So when we plug in negative 100, that's negative times e to the 1 over negative 100. Doesn't matter what you plug in, the output will always be positive for exponential. So this, oops, why did I write negative 1? I just meant to write positive. E to any number, it's always going to come out to be positive. So negative times a positive is a negative. So this right now, student, is negative. And then we have an asymptote at x equals to 0. Then we only have 1 left. Okay, let's see what happened when I plug in 1. I'm going to leave a little space right there. It's 1 times e to the 1 over 1, so that's 1 times e. So 2.718-ish, so 2.7, so it's positive. Well, on the right or left of that, I'm not sure if it's going to be positive or negative. So I'm going to go in and plug in 1/2. And I'm going to go in and do right end behavior, just like that. 100 times e to the 1 over, so 100 is positive, times e to the 1 over 100, that's also positive, so this is positive. Then I'm going to plug in 1/2, so let's see, that's 1/2 times e, 1 over 1/2 is e squared, okay. E squared, e is about 2.718, so think of it as, and then divide by 2, so I'm going to give you a decimal really quickly. E squared, oops, divided by 2 is going to give me 3.7-ish, okay. 3.7-ish, so it's slightly higher than e. So guys, if we have to look at this, it's going to be something like this, up and then here and then back up, just like that, okay. On the right side, everything is below, so must have been something like this. I don't know exactly what it looks like, but that would be my guess. So right now we would know your one local minimum right away. Let's confirm that really quickly with our derivative. We want f prime left end behavior. We knew f prime of 0 was not going to happen, so that's an open circle. We want in the middle, so that's f prime of 1/2 to see what that is. We knew f prime of 1 was 0, because that's how we got it, so that's closed. And then we want to do f prime up to the right side, just like that. All right, so here's f prime. All right, guys. Let's check it out. So on the top, we have negative 100. Okay. Now on the top, we could technically use this factor form here. On the bottom, it's always x, so that's always negative here for the negative 100. Well, we can just write negative sign, right? Just like that. On the top, e to the 1 over negative 100, that's always positive, times negative 100 minus 1, that's negative. So on the top, you would have a positive times a negative is going to give me a negative divided by negative, so that's positive. So this is positive. All right, let's do 1/2. E to the 1/2, this is just the numerator. E to the 1 over 1/2 is e to the 2. All right, so e squared, that's, and then we got 1/2 minus 1, that's going to be negative. And then this is now divided by 1/2. So you guys can see that this is going to reduce a little bit. So I should have a negative e squared. So that's going to be somewhere down here. Then we're going to pick 100, okay? So e to the 1 over 100, that's positive. 100 minus 1, it's also positive. All over, x is the denominator, that's positive, so this is positive. So that's all positive right there, guys. So let's answer all the questions that they asked us earlier. When is it increasing? It's increasing when your f prime is positive, and they are here. So that's going to be from negative infinity. 0 cannot happen, so you cannot use bracket here, even if you really, really wanted to. Union that with, at 1, it's from 1 to infinity, okay? At 1, you can pick parentheses as well, okay? So this could also look like this, okay? Decreasing is B. It's when f prime is negative and it's gonna go from 0 to 1, just like, oh, sorry, 0, do not use bracket at 0. Whoops, big no-no, because that was not, that doesn't even exist, okay? You can use bracket here at 1, or you can use parentheses at 1. Then we want to know about local max or local min. That was L max. Okay. We do not have endpoints, so I'm not going to give you the definition of endpoint, but L max is when the derivative goes from big to negative, go from positive to negative. So let's see. I have one location, okay, when the derivative goes from positive to negative. So at x equals to 0, but, right, f of 0 doesn't exist, so we have none. So no L max. And then I'm going to put a star because f of 0 does not exist. Okay, then let's do L min. L min by definition is when the derivative goes from a negative to positive. Okay, so I do have one spot where it goes from negative to positive, so that's at x equals to 1. So L min is blank at x equals to 1. Let me go to my chart and see. Oh, okay. So when f was 1, we got E. So it's E. So guys, those are the answers.